The universe is huge, and we're still puzzled about how it came to be. Figuring out why it's growing and how much it's expanding is a big mystery for scientists. Our rules and what we know seem to fall apart when we try to find the universe's end or its limits. Initially, we believed that gravity would put a halt to the universe's expansion, since it was expected to be the dominating force controlling the process. But when scientists looked at faraway light, they saw something surprising. Instead of slowing down, the universe was getting bigger, even faster than the speed of light. That's a big deal, because the speed of light is supposed to be a limit to how fast things can go. This raises a bunch of questions. Does the universe even have an end? What lies behind the universe's relentless expansion, defying the very laws of gravity? And the answer to all this question lies in an enigmatic force, concealed from our sight, yet wielding profound influence over the cosmos. It's the elusive dark matter, shrouded in mystery and intrigue. Join us as we embark on a journey to unravel the secrets of this cosmic enigma, peering into the abyss to uncover the hidden truths that govern the universe. In the vast expanse of the universe, there are clouds of matter composed mainly of hydrogen, helium, and dust drifting through space. Unlike on Earth, there's no weather or wind to stir these clouds. Nevertheless, gravity exists, leading each particle of matter to exert a slight attraction on every other particle, albeit with minimal force. Over incredibly long periods, these particles gradually draw closer to one another. Initially, there's only a small amount of matter in any given space, but over immense periods, these fragments start to gather together. Once matter begins to clump, its gravitational pull increases, attracting more gases. Eventually, if there's enough matter, it forms a dense object. This mass of matter presses inward, and as more particles collide with it, their kinetic energy from gravity transforms into heat. Similar to rubbing your hands together to create friction heat. This process happens incredibly slowly, but over time, the mass grows larger and denser. After millions of years of heating up, something extraordinary happens. The ball, now containing billions of tons of matter, reaches a crucial point. Most of the stuff in this ball is hydrogen, the simplest element in the universe. Due to the immense gravitational pull, the hydrogen atoms or hydrogen ions, stripped of their electrons due to the intense heat, are squished together tightly at the core, where temperatures are extremely high. Now, here's where things get really interesting. These hydrogen ions behave in a weird way because they're quantum particles. Instead of following the usual rules of physics we're used to, they follow the rules of quantum mechanics, discovered in the 1900s. One cool thing about quantum particles is that, until they bump into something, we can't say exactly where they are. This means they can kind of jump around without going through the space in between. It's called quantum tunneling. Normally, these positively charged hydrogen ions would repel each other because of electromagnetism. Even with all the heat and pressure, they can't get close enough to interact. But thanks to quantum tunneling, a small bunch of them jump close to each other. When they do, the strong nuclear force, which only works over tiny distances, kicks in and pulls them together more strongly than electromagnetism pushes them apart. If they get past this point, they fuse together to form a new kind of ion, helium, the next element on the periodic table. In this process, a little bit of stuff turns into a lot of energy. The famous equation for this is E equals mc squared, where E stands for energy, m for mass, and c for the speed of light. The speed of light is really fast, so even a tiny bit of stuff can make a huge amount of energy. If you could change 1 kilogram of matter into energy, you'd get as much energy as a power station makes in 6 years, all at once. When fusion starts, there's a huge burst of energy, which comes out as light, and that's when the magic begins. A star is born, igniting the cosmic stage with its blazing brilliance. Stars are super important in the universe. Just look up at the night sky. Except for the moon and a few planets, it's all stars. With strong telescopes, we can see billions of them. Unlike planets and the moon, which shine from sunlight bouncing off them, stars make their own light. They also make heavier elements over time. Some stars explode when they're old, spreading heavier dust into space. If only stars formed from clouds of matter, the universe would still be amazing. But no one would be around to see it. Life as we know it can't exist on or in a star. But not all matter near a star gets sucked into it. Most does. The sun has over 99% of the stuff in our solar system. But there's still a lot of matter left around the star. Over time, this matter might fall into the star, but at first, it spins around. It ends up forming a flat disk around the star, called an accretion disk. In this disk, similar things happen as when stars form. Particles come together to make bigger and bigger things, eventually forming planets. Sometimes another star forms, making a binary system where 2 stars orbit each other. The parts of the disk around a second generation or later star tend to make rocky planets, like Earth. Where there's less heavy stuff, the planet is mostly gas, like Jupiter or Saturn. Even though planets don't get as hot as stars, they still warm up as new stuff hits them, usually getting hot enough to have a molten core, like Earth's, which stays molten because of radioactive elements inside it. So, these are the key ingredients of the universe on a medium scale: planets and stars. For a while, people believed these were the biggest building blocks the universe had. However, since the 1700s, there have been suspicions about blurry patches in the sky, later known as galaxies, without the same spinning effect that keeps matter around a star from falling into it. All the stars in a galaxy would likely merge into one massive lump due to gravity. But like stars, galaxies also spin, which keeps them in a disc-like shape, often spiral, resembling swirling liquid draining down a sink. Additionally, there are groups of galaxies, clusters and superclusters, forming even larger structures across the universe, like the Coma cluster, which led scientists to speculate about dark matter. With the discovery of galaxies, we now have the fundamental elements needed to understand the universe: stars as the central players, planets orbiting stars, and galaxies made up of star collections. Of course, there are many other intriguing aspects of the universe to explore, which we'll delve into later. But for now, we've met the essential components necessary to ponder matter and to put the discovery of dark matter into context. There are about 10 to the power of 80 atoms in the visible universe. That's a huge number with 80 zeros after it. Yet, almost all of this matter is made up of just 94 elements. While chemistry enthusiasts might recognize a few more, those extras aren't naturally occurring. We have a pretty good idea of where these elements come from. Hydrogen and a bit of helium and lithium were likely formed after the Big Bang, when the universe cooled enough for matter to form. Heavier elements, up to iron, were forged in the fiery hearts of stars through nuclear fusion. But what about elements heavier than iron? They're mainly produced during supernova explosions or from the intense collisions of neutron stars. Now, let's simplify things even more. All atoms, regardless of their element, are composed of just 4 basic parts: electrons, protons, neutrons, and gluons. The central nucleus contains protons and neutrons, while electrons orbit around it. Then there's the photon, which makes up light in all its forms, from radio waves to gamma rays. If you dive into particle physics, you'll find even more particles, like different types of quarks, neutrinos, and bosons. These particles are essential for understanding reality, but they're like background characters in the grand story of the universe. But there's a puzzle. The way galaxies rotate suggests there's something more, something beyond what we know in particle physics. The dark matter. Despite its name, dark matter isn't actually dark. It doesn't interact with light at all, but has a gravitational pull. It's like transparent matter, invisible to electromagnetic forces, but still affecting the universe through gravity. Fritz Zwicky first noticed this effect, but it was largely overlooked at the time. Fritz Zwicky was a Swiss astronomer. He worked most of his life at the California Institute of Technology in the United States of America, where he made many important contributions in theoretical and observational astronomy. It took about 40 years after Zwicky's initial hypothesis for the concept of dark matter to gain traction. In the early 1970s, similar observations to Zwicky's were made regarding small satellite galaxies orbiting larger ones. However, the significant change in viewpoint occurred as a result of the contributions made by one of two notable female astronomers during the 1960s and 70s. One of these overlooked figures was British radio astronomer Jocelyn Bell, who discovered fast-rotating neutron stars called pulsars. Vera Rubin, another scientist who contributed to advancements in the understanding of dark matter, played a significant role in its progress. Rubin's pivotal contributions to dark matter research began shortly after she joined the Carnegie Institute in 1965. Collaborating with instrument maker and astronomer Kent Ford, Rubin utilized Ford's innovative device that electronically amplified visual input, enabling spectroscopic readings of galaxies in a fraction of the time previously required. During her earlier studies of galaxy rotation, Rubin made a startling discovery. Unlike a solid disk, where objects closer to the edge move faster than those near the center, the rotation pattern of galaxies did not follow this expected behavior. Instead, the speed of stars in galaxies remained constant even as the distance from the center increased, defying Newton's law of gravitation. This anomalous rotation curve challenged existing theories and hinted at the presence of unseen matter, ultimately leading to the revival of interest in dark matter. When observing the Andromeda Galaxy, Rubin and Ford noticed something surprising. The outer parts of the galaxy were rotating at nearly the same speed as the inner parts. This suggested the presence of a large amount of matter distributed in a spherical shape around the galaxy, forming what's known as a halo. Despite Andromeda being extensively studied, no visible halo of matter was found. Similar to Zwicky's findings, Rubin's observations hinted at the existence of dark matter due to its gravitational impact on the galaxy's rotation. Intrigued by this discovery, Rubin and other astronomers studied more galaxies and found the same pattern. Additionally, these galaxies were rotating so quickly that they should have flown apart if only the visible matter was accounted for. Rubin estimated that there was about 6 times more matter in galaxies than what was observed through visible material. As the idea of dark matter gained traction, astronomers utilized Zwicky's concept of using galaxies as lenses to provide additional evidence. The gravitational lensing effect, caused by the mass of a galaxy bending light, supported the presence of dark matter. However, the nature of dark matter remained a mystery. Traditional components of matter, like quarks and electrons, couldn't explain it, as they interact electromagnetically. So, what could be the alternatives? There have been many attempts to figure out what dark matter really is. Two main ideas are widely explored. One suggests dark matter is made of familiar particles from the standard model of particle physics, but with unusual behaviors, while the other proposes exotic particles that would expand the standard model. One significant candidate from the standard model is the neutrino, a particle theorized in 1930 and first directly detected in 1956. Neutrinos are produced during beta decay, a process where unstable radioactive elements emit electrons. Initially, scientists noticed that something was missing in the conservation of energy and momentum during beta decay, leading to the prediction of the neutrino. Neutrinos are elusive particles that hardly interact with matter and are nearly invisible. Despite trillions passing through our bodies every second, they rarely affect us due to their lack of electromagnetic interaction. Neutrino detectors, often located deep underground, occasionally catch interactions between neutrinos and other particles. These detectors typically consist of large tanks of fluid, such as water or tetrachloroethylene, where the few interacting neutrinos can produce detectable changes or bursts of light. Although neutrinos have been detected, they're not enough to explain dark matter fully. Their elusive nature and limited interactions suggest that other particles or phenomena may account for dark matter's presence in the universe. In the 1960s, scientists discovered that neutrinos come in three types: electron, muon, and tau. This explained why early attempts to detect neutrinos from the Sun only captured about 1/3 of the expected amount. The detectors could only identify one flavor. Neutrinos can change flavors while traveling, a process called oscillation, which suggests they have a tiny amount of mass. This mass makes them potential candidates for dark matter. But there are challenges. Neutrinos move too quickly to form the slow-moving halo structures needed for dark matter to shape galaxies. While neutrinos are fast-moving means hotter, dark matter is believed to be cold to form galaxies. However, neutrinos were briefly thought to travel faster than light, which could have challenged Einstein's theory of relativity. But this was later found to be an error. Although neutrinos move quickly, it's possible that larger galactic clusters formed first and later broke into smaller galaxies. To understand the universe's early structure, scientists study the cosmic microwave background radiation. Telescopes are extraordinary tools, acting as time machines that transport us back in time as we peer deeper into the cosmos. The farther away an object is, the further back in time we see it. For instance, when we observe the Andromeda Galaxy, situated 2.5 million light-years away, we're witnessing it as it appeared 2.5 million years ago. Theoretically, the limit of this cosmic time travel is about 13.5 billion years, reaching back to the moment when the universe transitioned from being opaque to transparent after the formation of atoms. Before this critical juncture, light was trapped by electrically charged matter. However, the light emitted at that time has undergone a dramatic journey due to the universe's expansion. As the fabric of space expands, it stretches the light waves passing through it, causing them to shift towards longer wavelengths, notably the red end of the spectrum. This phenomenon is akin to stretching a spring, where the further apart the coils become, the longer the spring appears. Consequently, the high-energy gamma rays emitted at the universe's dawn have gradually transformed into lower-energy microwaves over billions of years. This incredible discovery wasn't intentionally sought after. In 1965, Robert Wilson and Onno Penzias, while aiming to detect radio signals from the Milky Way, stumbled upon a peculiar background noise emanating uniformly from all directions. This enigmatic signal turned out to be the cosmic microwave background radiation, the ancient afterglow of the Big Bang itself, marking a pivotal moment in our understanding of the universe's origins. The strange signal Wilson and Penzias detected was akin to the fuzziness you'd see on old TV screens when they weren't tuned to a channel. That familiar hiss was exactly what they picked up. At first, they thought it might be interference from Earth, a common issue in radio astronomy. But after careful investigation, they realized it wasn't coming from any nearby sources and remained strong no matter where they pointed their antenna. Another culprit they considered was the buildup of pigeon droppings in their equipment. Despite cleaning up and shooing away the pigeons, the mysterious noise persisted. It wasn't until they spoke with other scientists that they realized the significance of their discovery. The microwaves they detected were remnants of light released when the universe became transparent around 370,000 years after the Big Bang. This radiation, known as the cosmic microwave background radiation, offers a glimpse into the universe's earliest stages. While it's often called the echo of the Big Bang, this phrase is somewhat misleading since it actually reflects events that occurred 1/3 of a million years after the Big Bang. Nonetheless, it provides invaluable insights into the universe's infancy, stretching back as far as light allows us to see. Although we can't observe beyond the cosmic microwave background radiation using current methods, advancements in technology offer promising avenues. Neutrino detectors, like the first neutrino telescope used to image the Sun, could potentially reveal cosmic neutrino background radiation from the universe's first seconds. Similarly, the detection of gravitational waves holds promise for further exploration. When Earth-based detectors, like the radio telescope used by Wilson and Penzias, examine the cosmic microwave background, it appears smooth, with consistent levels in every direction. However, recent satellite missions, such as COBE, WMAP, and Planck, have revealed subtle variations in intensity, offering a more detailed view. These variations, resembling an ultrasound of the universe's early stages, shed light on how galaxies formed. They also helped scientists rule out neutrinos as the primary source of dark matter and provided further evidence for its existence. Complex computer simulations by astronomers supported these findings, showing that the detected variations align closely with observations of galaxies and clusters. After eliminating neutrinos as potential candidates, the focus shifts to two quirky acronyms: WIMPs and MACHOs. WIMPs, or weakly interacting massive particles, and MACHOs, which stand for massive compact halo objects, suggest that dark matter could be invisible ordinary matter, as first speculated by Fritz Zwicky. This encompasses everything from dust to black holes. However, the evidence against MACHOs is substantial. One reason for considering dark matter is the apparent surplus of mass in the early universe compared to ordinary elements. If dark matter were just unseen ordinary matter, this disparity wouldn't exist. Moreover, it's puzzling why this unseen matter would form spherical halos rather than the flat disks typical of galaxies. Efforts to detect MACHOs beyond the halo by observing their gravitational lensing effects on light haven't yielded enough evidence to explain dark matter. Additionally, the distribution of dark matter often doesn't align with the formation of black holes, which should contribute significantly to MACHOs. Nevertheless, an alternative theory proposes the existence of primordial black holes. These black holes might have formed during the universe's infancy, when violent fluctuations in spacetime following the Big Bang compressed matter to create them. These primordial black holes could range from microscopic entities to colossal masses. Different arrangements of these black holes have been simulated to propose that relatively lightweight ones, with masses typically ranging from 0.06 to 1 times the mass of the Sun, might create some of the effects associated with dark matter. However, a study from the University of California in 2018 examined 740 supernovas to search for gravitational lensing caused by primordial black holes. Their conclusion was that no more than 40% of dark matter could be made up of black holes, and it's likely that none of it is. So far, there's no proof that such black holes exist or contribute to the effects of dark matter. However, there's speculation that the LIGO gravitational wave detector might eventually detect mergers involving these unusually small black holes. If this happens, they could become relevant again in the ongoing quest to understand dark matter. But for now, the focus remains on WIMPs as macho particles take a backseat. Initially, scientists focused on weakly interacting massive particles in the search for dark matter. WIMPs were thought to be heavy particles that interact weakly with regular matter, fitting the idea that dark matter must have mass to affect gravity. They were expected to have a similar weight to the Higgs boson, a particle discovered at CERN in 2012. The Higgs boson is known for its role in giving particles mass, though it doesn't directly provide mass itself. Instead, it's associated with a field in the universe called the Higgs field. Interactions with this field contribute to the masses of other particles. The discovery of the Higgs boson confirmed the existence of this field. The notion that dark matter particles might share a mass similar to the Higgs boson comes from theories about how particles formed in the early universe. As the universe cooled, the energy available for creating heavy particles decreased, leading to a preference for particles with masses like the Higgs boson. Despite efforts, experiments at the Large Hadron Collider and studies of cosmic rays haven't found dark matter particles directly. Instead, scientists look for secondary particles generated from interactions. These experiments involve the conversion of energy into matter, following Einstein's famous equation E=mc². But for now, researchers are on a quest to find WIMPs. If they succeed, then the revelation about the dark matter may be done. One more idea floating around is the antimatter hypothesis. Just like matter, antimatter exists with opposite properties, such as electrical charge. When matter and antimatter meet, they annihilate, producing energy in the form of light photons. Some researchers speculate that a similar process might occur between dark matter and its counterpart, anti-dark matter. However, this idea comes with many ifs. If anti-dark matter exists, and if the collision of dark matter and anti-dark matter produces energy that creates ordinary matter and antimatter particles, we should be able to detect these particles. If we observe more particles than expected from the collision, it could be from dark matter. It's important to note that dark matter particles are not expected to be Higgs bosons or regular atoms. They would interact differently with other matters. Instead, the focus has been on a theory called supersymmetry, which suggests that each known particle should have a more massive partner particle. In particle physics, particles fall into two categories: fermions and bosons. Fermions, which include matter particles like quarks, electrons, and neutrinos, follow the Pauli exclusion principle and don't like being too close together. On the other hand, bosons, like photons, which carry forces including electromagnetism and light, can occupy the same space without issues. It might seem like there are already plenty of particles to explain everything, but many theorists are hoping for more. Supporters of string theory, which aims to merge quantum theory and general relativity, anticipate the existence of supersymmetric particles. These particles are crucial for most versions of string theory to function. Supersymmetry proposes that every known particle has a counterpart of the opposite type. Each fermion should have a boson partner, and each boson should have a fermion partner. For instance, a quark's supersymmetric boson partner is called a squark. and a photon's supersymmetric fermion partner is a photino. However, none of these partner particles have ever been discovered, despite the elegance of the theory. If supersymmetric particles exist, some suggest that neutralinos, predicted to be the lightest among them, could be the particles responsible for dark matter. Neutralinos are thought to arise from a mix of quantum states of supersymmetric partners of neutral bosons like the photon, C particle, and Higgs, known respectively as the photino, CNO, and Higgsino. Again, there's no experimental proof supporting this idea. But neutralinos appeal to theorists because calculations suggest their emergence aligns well with the estimated mass of dark matter in the universe. Efforts to detect remnants of dark matter or anti-dark matter annihilation, using dedicated satellites and experiments on the International Space Station, have yielded nothing conclusive. While these experiments have uncovered new information about conventional matter events, like unexpectedly high radiation levels from the galaxy's center detected by the Fermi satellite, using such data to draw conclusions about dark matter is akin to speculating about alien technology based on unidentified flying objects. It's more likely that these UFOs are ordinary flying objects yet to be identified. And assuming they can teach us about aliens belongs in the realm of science fiction rather than science fact. The absence of experimental evidence for WIMPs shouldn't be surprising since dark matter interacts only through gravity, which is too weak to detect individual particles. However, if WIMPs existed, they should be detectable in colliders and through their decay products, but no such detection has been made. Likewise, experiments searching for their interactions with ordinary matter, similar to neutrinos, haven't found any evidence of WIMPs. To be clear, evidence supporting the existence of WIMPs hasn't been strongly confirmed, but there have been claims of detection. Scientists have set up various experiments to find these dark matter particles. Some detectors are placed deep underground, similar to neutrino experiments, to avoid picking up other particles accidentally. Researchers watch for unexpected collisions with particles that don't usually interact. They use devices like squids or scintillation detectors to observe the outcomes of these collisions. Squids, or superconducting quantum interference devices, detect tiny changes in magnetic fields using a quantum structure called a Josephson junction. These devices must be kept very cold to work properly. When a dark matter particle collides nearby, it can generate a small amount of heat, disrupting the superconductivity briefly. Detectors based on scintillation notice a brief flash of light when a collision gives energy to an electron in the detector's fluid, causing it to emit a photon of light. Most of these experiments, whether using squids or scintillation, haven't found anything significant, despite a few false alarms. For example, the CDMS experiment at Stanford University initially failed due to inadequate shielding from natural particles. Its successor, CDMS-2, and later detectors like Super CDMS, were moved underground to reduce interference. In 2007, CDMS detected 2 potential interactions, but they couldn't confirm if they were from WIMPs. Another experiment called DOMA, located in Italy, detected possible dark matter particles, but their results couldn't be replicated. Even with similar experiments like COSMOLOGICAL, no confirmation of DOMA's findings has been made. This shows how challenging it is to rule out false readings from these sensitive devices. These detectors can't directly see the particles they're looking for. Researchers infer their presence from the effects on other particles in the detector. Eliminating other causes for these effects, such as natural radioactivity or neutrinos, isn't easy. In addition to burying detectors underground, scientists need to come up with clever ways to keep out unwanted interference and to identify dark matter activity. Sometimes, the methods used for shielding can be quite unusual. For instance, one detector used lead from an old French ship's hull, lead is effective at blocking regular radiation, and because this lead was old, it had lost much of its own natural radiation over time, reducing background noise. The hope was that dark matter could be distinguished from other radiation because it's not evenly spread out, so there should be periodic highs and lows as the Earth and the solar system move around their orbits. However, these variations haven't been observed yet. In early 2019, a team at the University of California, Davis claimed to have found a possible explanation for why DOMA's occasional detections couldn't be replicated by other detectors with similar or better sensitivity. If true, it would be similar to the case of the spurious faster-than-light neutrinos, where the culprit was a technical error. The DOMA detector consists of cylindrical scintillators with a device called a photomultiplier tube at each end to amplify light. The Davis team found that even a small amount of helium contamination in the photomultiplier could mimic detections. Although DOMA's readings do show variation between summer and winter, suggesting an external source like dark matter rather than internal radiation, helium can be produced by the decay of radon and other geological processes, which also varies seasonally. Several methods have been proposed to distinguish between contamination and dark matter, but none have been put into practice yet. As of early 2019, the latest detection experiments, such as Xenon 1 Tesla in Italy's Gran Sasso National Laboratory and Pandax in China's Jinping Underground Laboratory, both using xenon in liquid and gaseous forms for scintillation, have reported no findings. Xenon 1 Tesla even achieved a record low background level, indicating that it had effectively ruled out alternative sources of events, making the lack of dark matter detection more significant. Another idea gaining traction is to search for fossil evidence of past impacts from dark matter. Instead of waiting for dark matter to interact with underground detectors, scientists propose examining minerals that have been buried for a long time to see if they show any signs of being struck by dark matter particles. These impacts could leave behind tiny tracks due to the recoil of atoms from the collision. The concept of finding fossilized impact traces underground dates back to the 1980s when experiments aimed to detect the impact of magnetic monopoles, but they were unsuccessful. In the mid-1990s, a similar idea was proposed to look for traces of potassium atoms recoiling from dark matter impacts in mica minerals, but it was never tested. However, in a 2018 paper from researchers in Sweden, the USA, and Poland, the idea was revisited. The recent study explored using other minerals like halite, a type of sodium chloride, epsomite, olivine, and nickel bischofite. So far, researchers have only estimated the sensitivity of detectors using these materials, and it's uncertain whether they will be put into practice. The continued lack of results from other detectors might prompt consideration of this approach, despite its theoretical potential for greater sensitivity. While WIMPs are still the leading candidates for dark matter particles, the failure to find them and the inability of machos to explain observations have led theorists to consider more exotic alternatives. Another potential candidate for dark matter is the axion. Despite its name sounding like a household cleaning product, it was actually named after a dishwasher detergent. Theoretical physicists have proposed the existence of axion particles to explain certain quirks in quantum physics, although there's no experimental proof of their existence yet. Axion, if they exist, are predicted to have limited interactions, low mass, even lighter than neutrinos, and are thought to be abundant in the universe. However, they face challenges as a solution to dark matter. Like neutrinos, they might be too hot to fulfill the role of dark matter, and some theories suggest they would form structures that haven't been observed. Efforts to detect actions have been made through experiments like the Axion dark matter experiment, set up in the 1990s at the Lawrence Livermore National Laboratory in California. The experiment used a highly sensitive radio receiver to detect photons produced by actions when passing through a strong magnetic field. However, Despite running for several years, ADMX didn't detect any actions. Whether we're considering WIMPs or actions, attempts to identify a specific dark matter particle rely on certain assumptions that might not hold true. We understand how regular stuff and forces in the universe work pretty well. This standard model describes most particles we know about, totaling 17 types. But some scientists think there might be 17 more types called supersymmetry. This model covers most of what we can observe. However, assuming that dark matter, which makes up 5 times more of the universe than regular matter, consists of just one type of particle seems like a big leap. We don't have any strong evidence for this assumption. It's mainly for the sake of simplicity in theories. The universe isn't known for being simple, after all. Dark matter could actually be made up of many different types of particles instead of just one. To put it another way, if we were living in a universe made mostly of dark matter and tried to figure out what regular matter was made of, we might wrongly assume there's only one type of particle, which we'd call an ordinarion. But that would be far from the truth. Some physicists call this assumption ordinary matter chauvinism because it implies that our kind of matter is more complex than dark matter. We can even imagine a parallel universe made of dark matter, with dark suns shining dark light onto dark planets inhabited by dark beings. But in reality, dark matter probably doesn't interact much with itself apart from gravity, so these dark matter worlds might not be very exciting. Still, it's fun to think about. Even though the idea of a dark universe is unlikely, some scientists have thought about how a dark photon, a photon with mass, might behave. This hypothetical particle could be a force carrier between dark matter particles, which themselves would be very light. If such a particle existed, it might cause tiny movements in mirrors used in detectors like LIGO, which detect gravitational waves. Detecting these movements could be possible with a future detector called LISA. But it's important to remember that this idea is based on a lot of guesses and might just be a way to improve gravitational wave detectors rather than something with a high chance of success. One more possible idea for dark radiation is something called a sterile neutrino, but keep in mind this is still very uncertain. Regular neutrinos are unlikely to be the main component of dark matter, but an experiment at Fermilab called Mini-Boon showed some clues in 2018. It suggested there might be an extra type of neutrino, called a sterile neutrino, because muon neutrinos seem to change into electron neutrinos through a mysterious intermediate state. Adding the sterile neutrino to our understanding of particle physics would require a big update to the standard model, mainly because it doesn't interact with a weak force like regular neutrinos do. In theory, if the sterile neutrino exists, it could possibly be a carrier of dark matter, but we're far from being sure about this. Still, it's an interesting idea worth exploring further. In 1983, astrophysicist Mordechai Milgram shook up the conversation about dark matter with a theory that could explain some of its effects without needing to introduce new kinds of matter or change the standard model of particle physics. Milgram, born in Romania in 1946 and based in Israel, named his idea Modified Newtonian Dynamics, or MOND, for short. His idea is straightforward but influential. It suggests that the effects attributed to dark matter could be observed if gravity behaved slightly differently on the scale of galaxies and clusters compared to smaller scales like planets and stars. This challenges the assumption that gravity acts the same on all scales. The adjustment needed to Newton's predictions would be small, but could explain why fast-rotating galaxies stay together when they should fly apart without any extra matter present. We're used to thinking of gravity as the same everywhere, but we know other physical behaviors change depending on scale. For example, matter behaves differently at the level of tiny particles than it does at the human or planetary scale. We've even had to adjust Newtonian dynamics slightly to fit with Einstein's general theory of relativity, which gives similar results overall, but with some differences in specific situations. Initially, Milgram's idea posed a serious challenge to the idea of dark matter until the discovery of the bullet cluster. One of the strongest pieces of evidence for dark matter is the bullet cluster, named for its shape resembling a bullet trailing its gases. This cluster appears to be the result of two galactic clusters colliding. It's shaped like a blob with two bulging outer regions, often likened to Mickey Mouse ears. Though it's important to note these regions are three-dimensional, not flat. It's hard to explain this unique structure just with the collision of regular matter clusters. The idea is that during the merger, ordinary matter collided in the center, releasing energy as high-energy light. This caused the ordinary matter to stay put around the central point of impact. However, dark matter doesn't interact through electromagnetism, so it passed through this central region and continues moving. Gravity eventually slowed it down, but not before it spread out on either side of the central area. This resulted in two outer lobes made mostly of dark matter, attracting enough regular matter to be visible, along with a central segment mainly composed of ordinary matter. This explanation is why the bullet cluster is significant to many cosmologists and astrophysicists. It's seen as strong evidence supporting dark matter, effectively ending the debate over modified Newtonian dynamics. However, some argue that the bullet cluster doesn't settle the debate entirely. Supporters of modified gravity theories are gaining more traction than before, indicating that the discussion isn't as clear-cut as some may think. The truth is, while the basic version of MON struggles to explain the bullet cluster, there are also other cosmic phenomena where dark matter doesn't seem to fit well as an explanation. In these cases, it makes more sense to consider a modified theory of gravity instead. Take the galaxy NGC 1560, for example, discovered way back in 1883 and located about 10 million light-years away from us. The way this galaxy rotates doesn't match what we'd expect from Newton's theory. It needs something else to explain it. MON's predictions fit this curve really well, but the predicted curve from dark matter just doesn't match reality. So, the bullet cluster isn't the be-all and end-all evidence for dark matter. There are other examples, like NGC 1560, where a modified gravity approach works better. Newer modified gravity theories, like scalar tensor vector gravity, seem to handle the bullet cluster fine. And with another cluster, called the train wreck cluster, dark matter doesn't seem to explain things well, while STVG does. Another challenge to MOND comes from a dwarf galaxy called NGC 1052 DF2, discovered in 2018. It seemed to be rotating without any dark matter, which is unusual but possible if dark matter exists. The assumption in dark matter theory is that all galaxies need it to form, but maybe it can be stripped away by interactions with other galaxies. However, if dark matter isn't there and galaxies behave because of some modified gravity theory, then a normal galaxy without dark matter shouldn't exist. Initially, NGC 1052 DF2 was seen as evidence against modified gravity, but things are more complicated. With more analysis, the galaxy's behavior doesn't seem different enough to really challenge even basic modified gravity theories. At the moment, the discovery of NGC 1052 DF2 is still up in the air. Another group suggests the data was misinterpreted and the galaxy does have dark matter after all. They think maybe the galaxy is closer to us than we thought, which would change our calculations about its mass and whether it has dark matter. So, we're still waiting for more evidence to come in. MOND and its newer versions aren't the only options when it comes to changing our understanding of gravity to explain the effects attributed to dark matter. A new player in this field is emergent gravity, also known as entropic gravity. Our current main theory for gravity is Einstein's general theory of relativity, which has held up well over time, except for its struggle to mesh with quantum physics. Attempts to combine the two often run into mathematical problems. Some approaches, like loop quantum gravity, tweak general relativity to allow for a quantum description of space-time. Emergent gravity is the latest take on this, drawing on the idea that general relativity shares similarities with thermodynamics, the science of heat and gas motion. In this model, gravity isn't seen as a fundamental force but emerges from entanglement between quantum particles of space-time. This concept of emergence is common in nature, where simple parts come together to form complex systems, like sand dunes, snowflakes, or living organisms. However, making gravity emergent is a big leap. In 2016, Dutch physicist Erik Verlinde suggested that if emergent gravity were real in a universe like ours, it would cause deviations from general relativity, leading to effects similar to those attributed to dark matter. This effect would mainly affect less dense systems like galaxies, rather than denser ones like solar systems. But there are challenges. This theory is still new and not fully fleshed out. Its predictions don't match observations as well as MOND in explaining how matter moves in galaxies, and it's not as good as dark matter at explaining the behavior of clusters. Plus, it doesn't yet shed light on large-scale structures or how structures formed in the early universe. Despite its limitations, emergent gravity sparks interesting ideas and emphasizes the importance of considering modified gravity theories alongside traditional ones. The ongoing effort to detect dark matter will undoubtedly continue as no definitive results directly related to it have been confirmed yet. Previously, the field of cosmology, which delves into the study of the entire universe, predominantly relied on speculative theories rather than empirical evidence. Origin narratives often stemmed from religious or philosophical ideologies, lacking substantial experimental or observational support, resembling more of speculative fiction. However, a significant shift occurred on January 8, 1998. When representatives from various research groups unveiled what they deemed as conclusive data, transitioning the study of the universe from mere speculation to a scientific endeavor. Notably, theories such as the Big Bang have undergone adjustments over time to align with empirical observations, reminiscent of how Aristotle's model of the universe was augmented with epicycles. Despite the widespread acceptance of the Big Bang theory with inflation, there exist reservations among some physicists regarding its foundational aspects, particularly inflation, which lacks robust justification. Nevertheless, the announcement in January 1998 marked a pivotal moment. Saul Perlmutter underscored the significance of data-driven cosmology, signaling a departure from philosophical conjecture. The data indicated the ongoing expansion of the universe and hinted at the presence of a mysterious entity driving this expansion. Interestingly, the mysterious entity was initially proposed by Einstein as a fudge factor to stabilize his equations in the general theory of relativity, referred to as the cosmological constant, symbolized by the Greek letter lambda. To grasp the importance of the cosmological constant, it's essential to delve into Einstein's general theory of relativity. His groundbreaking work from the early 20th century elucidating gravity as the curvature of space-time induced by matter. In essence, his equations delineate the correlation between the curvature of space-time and the mass energy causing it. Initially, Einstein's equations did not encompass the cosmological constant denoted by lambda, but he later introduced it to counteract what he perceived as an error. He envisaged a static universe where gravitational force offset the expansion or contraction. However, this endeavor proved futile, as even a minor perturbation could disrupt this equilibrium, prompting Einstein to dub the constant his greatest mistake. For decades, scientists operated under the assumption that the cosmological constant was zero. However, the 1998 announcement revolutionized this perspective, revealing the necessity of a significant cosmological constant to elucidate the accelerating expansion of the universe. The accepted value for the cosmological constant is approximately 10 to the power of -52 per square meter. While this advancement represented a move towards a more scientific understanding of cosmology, the perplexing issue of the cosmological constant's value persists, posing a challenge to current models. Even after more than 2 decades, this enigma persists, prompting an in-depth exploration of quantum physics. In 1927, German physicist Werner Heisenberg introduced the uncertainty principle, a cornerstone of quantum physics, postulating that certain aspects of reality at the quantum level are intrinsically interconnected. This uncertainty intimates that when observing a brief time frame in empty space, the energy within it can fluctuate significantly, occasionally giving rise to matter. Quantum physics posits that empty space teems with virtual particles that spontaneously emerge and vanish before detection. This phenomenon finds validation in the Casimir effect, where 2 adjacent metal plates are drawn towards each other due to the surplus of virtual particles outside compared to the limited space between them. Hence, empty space was theorized to harbor energy, known as vacuum energy when averaged out. It was conjectured that this energy might propel the cosmological constant, now identified as dark energy. However, predictions using quantum field theory suggest a cosmological constant far exceeding the observed value, indicating a profound discrepancy between theory and observation. As data accumulation progressed, the initial assumption that the cosmological constant, lambda, was zero appeared reasonable. However, the early measurements from 1995 to 1997 were fraught with significant uncertainty due to factors like dust and measurement limitations. Although this assumption seemed to align with the data initially, various alternative possibilities also emerged as viable. Emerging techniques, incorporating diverse filters to mitigate dust effects, gradually gained prominence. With an influx of supernova observations, particularly from greater distances in time, it became apparent that the initial assumptions were flawed. Upon integrating more precise data from the Hubble Space Telescope, a shift in distribution occurred. The observed supernovas appeared dimmer than anticipated for their level of redshift. Despite initial hesitancy, the Berkeley team published their dissenting findings in Nature in October 1997, followed by the Heisey team. This challenged the notion of a universe devoid of a cosmological constant and possessing merely sufficient mass to account for phenomena. The tension among the teams in late 1997 underscored cosmology's distance from attaining maturity as a science. Many researchers resisted the notion of a cosmological constant, endeavoring to discredit it. A revealing email exchange within the Heisey group exposed this reluctance to embrace the concept. By February 1998, tensions reached a climax at a conference attended by both teams. While some advocated for cautious conclusions, pressure mounted as the press focused on the SCP group's data. Eventually, the Heisey spokesperson unveiled their findings, affirming the existence of the cosmological constant. Responses to this announcement varied. Some embraced the cosmological constant despite its divergence from quantum theory predictions, as it bolstered the rapid inflation hypothesis and the universe's age. Others sought alternative explanations, acknowledging the reliability of the data while underscoring the interpretational challenges inherent in cosmological observations. We've uncovered another mysterious element alongside dark matter. It's called the cosmological constant. However, there was still one missing element that we had been referring to as the mysterious entity. Let's uncover what this enigmatic entity truly is. Clusters of galaxies are like big gatherings in space, housing many galaxies, each wrapped in its own dark matter cloak. Surprisingly, the cluster itself holds a lot of dark matter, even more than all its galaxies put together. This dark matter controls how galaxies move and influences the hot gas spread throughout the cluster. Scientists figure out the hidden mass in a cluster by watching how visible stuff moves, similar to how they study galaxies. They also find out how much dark matter is in a cluster by seeing how its gravity bends light. By analyzing fluctuations in the cosmic microwave background and scrutinizing distant clusters such as the Bullet cluster, astronomers have determined that dark matter constitutes approximately 26% of the universe's overall mass and energy content. However, this raises a crucial question. If dark matter binds matter together, what force propels the expansion of the universe mentioned earlier in the video? Furthermore, what comprises the remaining portion of the universe? In the 1920s, astronomers, notably Edwin Hubble, observed that galaxies appear to be moving away from each other, with those farther away receding at greater speeds. This observation, combined with Einstein's general theory of relativity, led researchers to the conclusion that the universe is expanding, causing galaxies to drift apart. In 1998, two separate teams of researchers made a groundbreaking announcement. They had conducted highly precise measurements of cosmic expansion, revealing that it was accelerating. This newfound acceleration suggests the presence of an unidentified force opposing gravity, thereby causing the universe to expand at an increased rate. Astronomers focused their investigations on a particular type of supernova, known as Typeus supernovae. These explosive events occur within binary star systems, where one star is a white dwarf and the other is a companion star. Under specific conditions, such as when the white dwarf accumulates sufficient mass from its companion, it undergoes a runaway nuclear fusion reaction, culminating in a supernova explosion. During their study of these supernovae, researchers utilized the redshift technique. Contrary to expectations based on the assumption of a static or decelerating universe due to gravity, the supernovae appeared fainter and exhibited a redshift. Similar findings were corroborated by numerous scientists both prior to and following this experiment. Ultimately, scientists became convinced that the universe is not only expanding but doing so at a rate surpassing the speed of light. This extraordinary expansion was attributed to a mysterious force beyond the influence of both dark matter and gravity, termed dark energy. By computing the overall expansion, scientists determined that our universe comprises approximately 69% dark energy, with dark matter constituting 26%, leaving the remainder as ordinary matter. Unlike conventional matter, dark energy exhibits uniformity across both space and time and exerts a repulsive gravitational force within its spatial domain, in contrast to the attractive nature of gravity. However, the exact nature of dark energy remains poorly understood. Investigations into the impact of dark energy on the large-scale structure involve the measurement of subtle distortions in the shapes of galaxies, caused by the gravitational bending of space by intervening matter, a phenomenon known as weak lensing. Over the past few billion years, dark energy has become the dominant force in the universe, inhibiting the formation of additional galaxies and galaxy clusters. This shift in the universe's structure is discerned through weak lensing observations. Furthermore, assessments involve tallying the number of galaxy clusters to gauge spatial volume and the rate at which it is expanding. The primary objectives of observational studies on dark energy are to determine its equation of state, variations in its properties, and the extent to which it elucidates gravitational physics comprehensively. In cosmology, dark energy is a term that describes certain elements within the equations of Einstein's theory of general relativity. These equations connect the matter and energy content of the universe to the curvature of space-time. Both the density of matter or energy and the internal pressure contribute to how much gravity a component exerts. While familiar components like matter and radiation create attractive gravity by bending space-time, dark energy produces repulsive gravity due to its negative internal pressure. If the ratio of pressure to energy density is less than -1/3, which can happen when a component has negative pressure, it will push away from itself gravitationally. If such a component becomes dominant in the universe, it will cause the universe to expand faster. The simplest explanation for dark energy is that it's a kind of energy that fills empty space, sometimes called vacuum energy. Mathematically, vacuum energy is similar to Einstein's cosmological constant. Even though Einstein and others initially rejected the idea of the cosmological constant, modern physics, based on quantum field theory, suggests that vacuum energy naturally arises from the constant fluctuations of particles in empty space. However, the observed density of this vacuum energy is much lower than what's predicted by quantum field theory. This difference was known even before dark energy was discovered. While we haven't yet found a complete solution to this problem, some theories suggest that there may be many disconnected universes, and our universe just happened to have a value for the constant that allows for the formation of galaxies, stars, and life. The foundation of our understanding of the universe relies on observations made using type first supernovas as standard candles. Initially, there were doubts about their reliability. Unlike variable stars whose brightness directly corresponded to their timing of variation. However, researchers managed to calibrate the distances of supernovas by analyzing how their brightness changed over time. This calibration involved observing nearby supernovas, confirmed by other standard candles. But for the findings related to the cosmological constant, it was assumed that this calibration could also be applied to distant galaxies. Since distant galaxies are observed as they were billions of years ago due to the time light takes to reach us, any changes over time could affect the output curves of older supernovas, making our distance assumptions incorrect. Additionally, assumptions were made about the impact of interstellar dust on observations. A better understanding of dust's effects helped some groups catch up with others. However, dust remains a challenge in astronomy, as shown by difficulties encountered by other researchers. The BICEP 2 experiment at the South Pole reported evidence of gravitational waves from the universe's early moments. Unlike other forms of light, gravitational waves can pass through the universe unhindered, offering a unique window into the universe's early stages. If inflation occurred shortly after the universe's birth, it was predicted to generate primordial gravitational waves that would persist across the cosmos. BICEP 2 initially claimed to detect these waves, supporting inflation theory. However, doubts arose, and it's now understood that the signal was likely caused by dust, not gravitational waves. Similarly, in studying the cosmological constant, researchers had to correct for the influence of dust by accounting for its reddish spectrum and subtracting it from the data. Assumptions were made that dust's impact near us would be consistent with its impact throughout space. However, the presence of different types of dust, like gray dust, between early galaxies could explain the dim light from distant supernovas, challenging the concept of dark energy. At a 1998 press conference, uncertainties remained about the data. However, theorists suggested a way to investigate further. They proposed observing objects with higher redshifts, indicating they're further back in time, to see if differences emerged. This implied that the universe's expansion should have decelerated in the past, only accelerating once dark energy dominated. Observing supernovas in very distant galaxies could confirm this. Fortunately, the Hubble Space Telescope had already captured images crucial for this investigation, known as the Hubble Deep Field. Adam Riess, a Nobel laureate, made a breakthrough by analyzing data from these images. His discovery suggested dark energy had not yet dominated the universe over 10 billion years ago. Since Rees's revelation, various methods have been used to understand how the universe's expansion and dark energy have evolved over time. These include supernova observations, gravitational lensing of distant objects, and studying baryon acoustic oscillations. Despite these efforts, there's still no definitive theory explaining what dark energy truly is. Various theories have been proposed, but more research is needed to understand this phenomenon better. While the debate between dark matter and modified gravity theories continues regarding the stability of galaxies, there's another explanation proposed by mathematician Donald Sorry. Sorry suggests that dark matter might not actually exist and that astronomers have made errors in their calculations. We've always assumed it's possible to calculate how a galaxy moves, but this assumption is challenged when dealing with more than two interacting bodies. Predicting the motion of celestial bodies in our solar system has been done for centuries, but it relies on approximations rather than exact solutions. Now, consider a galaxy like Andromeda, with trillions of stars spread over vast distances. It's impossible to precisely track the motion of every star and how they influence each other. Instead, astronomers use a simplified model where the galaxy is treated as a continuous material, assuming each star orbits the galaxy's center of mass. While this method works for many predictions, it's not without flaws. The rest of the galaxy's effects are often ignored under this simplification. Sorry raises concerns about the approximation method used in calculations. Sorry is worried about how we calculate things. Imagine two stars orbiting close to each other near the center of the galaxy, because gravity gets stronger when things are closer together. Like when objects are near Jupiter in our solar system, the gravity between these stars is stronger than the pull towards the center of the galaxy. This means the faster star pulls the slower one along with it, which goes against what we assumed about how things move toward the center of the galaxy. Sorry suggests that since the equation commonly used struggles even with simple systems, it's unreliable for more complex settings like most galaxies. Despite this, Sorry still expects dark matter to be found, but not in the predicted distributions. He believes much of the search for dark matter might be a mathematical error, and suggests that while something labeled dark matter may eventually be found, it might not be what scientists expect. This challenges the conventional understanding of dark matter and adds complexity to our understanding of the universe. It suggests that dark matter might not be explained by unknown particles or modified gravity, but could be a mathematical illusion. This uncertainty about dark matter highlights the need for further investigation. As for dark energy, to understand it better, we need to explore how scientists discovered the size and expansion of the universe. Anyway, whatever may be the case, this enigmatic entity has attracted no less than black holes or pulsars. And with this, we are ending this fascinating topic. Thanks for joining me on this captivating journey into the enigmatic realm of dark matter. If you found this video as intriguing as I did, be sure to hit that subscribe button to stay tuned for more mind-bending content. Your support fuels my passion for exploring the unknown. So let's continue unraveling the mysteries of the universe together.